legközelebb. Jó. Na most így jó lesz. Ugye? Okay, so welcome everyone today on 1st of April of this year, and this is the subject again, dynamics of robot mechanisms, and we continue on with the Newton-Euler recursion, with which it's possible to calculate the kinematics of the robot in the forward iteration, and we can calculate the dynamics of the robot and the torques and forces in the backward iteration. So mainly today we focus on the backward iteration of the Newton-Euler recursion. So let's move on. Again, please make notes in your own notebook. It's better, it helps the understanding, and please ask if something is not clear. Thank you very much, and I think we can start. So from last time we create a drawing again. So last time we were talking about the geometric description, and in the planar case, for planar serial robot structure, we introduced a simplified notation, which is following the idea of the dinamikája convention, but it's simplified for planar case. Okay, so this is basically an illustration. And very similar to the dinamikája convention, but it is just similar, and it is not exactly the dinamikája convention. And the idea was that if we have two rigid bodies, we can describe the relative orientation and relative position of them with only two parameters instead of three. So basically there would be three independent parameters, because there is a motion in horizontal and in vertical direction, and also we have the rotation. So there is three independent parameters which describes the relative orientation, but if we use some constraints, then there will be only two independent parameters. So we said that this is rigid body I minus 1, and this is rigid body index I, and we said that a coordinate system is fixed to this rigid body, and we have x and y axis, and of course we also have axis z, which is always perpendicular to the whiteboard. So z is like this, and this is the origin of this coordinate system. And we have another coordinate system which is fixed to the other body, but the constraint is that the origin of the neighboring coordinate system must be on this line, which is the elongation of axis x of the previous link. So here we will have the origin of coordinate system I, and this is a translation, and additionally we have a rotation, so we can also rotate this coordinate frame, and this translation and rotation will give us two free parameters. We can choose them arbitrarily. So this is one parameter, which is the position difference of the two coordinate system origins, and the other free parameter is this angle here, which is theta I, and as we can see, AI is a translation along axis x, I minus 1, and theta I is a rotation. This is a rotation about axis zi, which is not shown yet, but now it's okay. Okay, so this was what we introduced, and with these two parameters we can describe the relative orientation of rigid bodies, and we said that we will have an example. So let's see the example which will help us to better understand everything. So we will use this notation in the example. And now we are still working with the kinematics. So this is still the forward iteration when we would like to describe the kinematics, and later the forces will come into the picture. So let's say that there is a bar which is fixed to the wall, and there will be a slider on this bar. So we have this kind of structure, and we say that the bar which is fixed to the wall is rigid body number 0 or link number 0, and then there will be a slider which can move in horizontal direction, and then there will be another bar which is fixedly or rigidly fixed here, so it is welded here, so they move together totally, and the length of this additional bar is b, so they move together and they form together rigid body number 1, or we can say link number 1. So link number 1 can move on in the horizontal direction, and then we can choose a coordinate which describe the position of this link here. So this will be Q1. Okay, this is our first general coordinate or first joint coordinate, and we will find the relation between the two parameters AI and theta I a bit later. First we draw the full structure. The second moving rigid body is tilted a bit, so this is a rod again, and there will be a slider, but that's another rigid body. So first just finish this this rigid bar. Okay, so this rigid bar will be link number 2, and it can rotate about this joint here, and the rotation angle will be our second coordinate, which is Q2. Okay, so this angle is our second joint coordinate. This is a rotational joint, and the second rigid body is this bar here, and there is a slider again on it, so this is a translational joint again. So rigid body number 3 is here, and the position of the third rigid body is given by this third coordinate, which is basically a distance, because we are talking about translation again. Okay, so these are our coordinates, and one more thing here. So there will be a point here which will be referred as tool center point. Okay, this is the tool center point of the robot, and it is rigidly fixed to rigid body number 3. Okay, so this whole thing moves together, and the parameter here is E. This is the length of this small bar. So this is our example, and let's go into the parameters. So as we can see, there are 3 moving bodies, 1, 2, 3, and therefore there are 3 joints. Basically, this is a translational joint, a revolute joint, and again a translational joint. So we can create 3 neighboring transformation matrices, and we can introduce these parameters. So there will be a table of parameters, and for each link, so we will have 3 links. This is link I, this is the index of the link, and we will have the parameter for the translation and the other parameter for the rotation, and we can create this table nicely. So we have 3 links, and for each link we will need the transformation, which is given by 2 free parameters, as we discussed before. But if we want to do that, first we should introduce some coordinate systems, but I would like to do it in a separate figure, otherwise it will be not really visible. So we will have a coordinate system for the global. So this is the fixed or global coordinate system, which is rigidly fixed to the ground or into the world. Okay, so this is the global coordinate system, and then we say that we fix another coordinate system to rigid body number 1, of which the origin is a bit moved in the horizontal direction, and now we know that this will be the origin of coordinate system number 1, but we see that the next coordinate system will be here, or we can just find out, and we know that again I have to draw this figure, unfortunately. So this is xi minus 1 and yi, and we know that we can only have a transformation along the axis x. Okay, so if we want to move later into this point, the axis x must be vertical, otherwise we cannot have a transformation with which we can move here to this point. So that's why this will be axis x1, and therefore the whole coordinate system is tilted. So y1 will be in this direction, and z1 is the axis about which we rotated the whole coordinate system. So this is basically fixed here. Actually we can just show the origins. Maybe this is O1, this was O0, and then we want to move here, this will be O2, this will be the origin of the second coordinate system about which we can rotate the whole rigid body. So this is O2 here. Again, we see that there is a translational transformation, and then there will be a rotation, and again we will have another coordinate system somewhere here, so the new x-axis must be in this direction, otherwise I cannot move our third coordinate system here. So that's why the axis x must be in this direction, and then it means that the y is in this direction, and z is always perpendicular to the whiteboard. So this is z2, and okay, so along these lines we can have a transformation. So now this is the origin, which is here in this figure, and we want to move our third coordinate system here. So this is O3 here, and if you want to move there, then we need again a translational joint, and no need to any other transformation. So x3 will be here, O3 will be here, and this y coordinate will be here. And again, we see that the tool center point is fixed here rigidly. This is TCP, and the meaning is tool center point, which is basically the grasper of the robot, or something with which it can perform the task. So we would like to position this point into the proper place. Okay, so this is the same robot with just showing the coordinate systems, and we should fill up this table. So as you can see, between the first two coordinate systems there is a translation, and this translation is called A1, but it is exactly equal to the first joint coordinate, so that's why A1 will be equal to our time dependent joint coordinate for the first joint. And then there is another parameter, which is the rotation. So again, I can show it here. So this is AI, and this angle here is theta I. So the rotation between this and this one is 90 degrees. So we say that this is pi over 2. So this was the first two parameters which give the transformation between these two coordinate systems. And then we go on. So we go from the first to the second, again with the translation, and this is B. And then there is also a rotation, but as you can see, first we have rotated back to this horizontal direction, the x-axis, and then with Q2 we can rotate for an arbitrary position. So this is minus pi over 2 plus Q2. So with which transformation, first we go here and then we go here, and then we can have a time dependent rotation angle additional to the minus 90 degrees. And then in the third transformation we go from here to here. This distance is Q3. So the third joint parameter, which is time dependent, is here, and we don't have any rotation between these two coordinates, so coordinate systems. So this is what we what we basically have, Q3. And the important thing is that for each transformation there is one parameter which is time dependent, and these time dependent parameters are the so-called joint variables or joint parameters, because these are representing the position of the joint, which is really a distance or an angle. Okay, so these are the so-called joint parameters or joint variables. So this is what we have, and if we know everything in this table, then we can fill up our transformation matrices. So as we said before, there is always a transformation matrix between coordinate frame I and I minus 1. Okay, and as we have seen last week, there is always a rotational part. So this is called a homogeneous transformation matrix, and one part is responsible for the rotations, and another part is responsible for the position difference. So this is the general form of this homogeneous transformation matrix, and we were filling up it last week. So it was looking like this. So there is always 3 0 here and 1 here, and as we said, this is the rotational part. So this is the cosine of the rotational angle theta I, and this is the sine of theta I, and sorry, this is 1 here, and this is 1 here. Okay, so this was the rotational part, and so Ci means cosine theta I, and Si means sine theta I. So this is what we have, and there is also a translation with parameter AI. So this is a translation along axis X. So this was our homogeneous transformation matrix between the two neighboring rigid bodies, and we have to basically take this table and fill up this matrix with the parameters, so we can create all of these neighboring transformation matrices. Homogeneous transformation matrices for the neighboring links. Which means that I will have a transformation matrix which transforms from the first to the zeros coordinate system, and then I will have another one which transforms from the second to the first, and then there will be another transformation matrix which transforms from the third to the second. So there will be 3 homogeneous transformation matrices, and we only have to fill them up based on this general formula and based on the variables, based on the value of the variables. And there is always a part which is not changing, so this is 0 0 0 1 in each case. And the other parts must be filled up. Actually this 0 0 1 is always the same, but let's go one by one. So in the first there is a rotation of 90 degrees, so the rotational part will be So cosine 90 degrees is 0, this is 1 here, and sine 90 degrees is 1. So therefore this is minus 1 and this is plus 1, and that's it. So this is the rotational part for the first transformation, which is 90 degrees rotation. And there is also a translation, which is basically our first joint coordinate q1. And we can show our joint variables again with red. Okay, so this is the joint variable, which is important. And then in the second, again we have some rotation, which is q2 minus 90 degrees. So because of this, you know, if you shift the angle with 90 degrees, then cosine will be sine and sine will be cosine. So finally it will be sine q2 and sine q2. Oops, it's too small. So it's in the next line, sine q2, and this is cosine q2, and this is minus cosine q2. So this was sine q2, and this is minus cosine q2, and 0, 0, 0, 0, and 1. So this is the second rotational part. And again we have a translation, which is simply b. So instead of a, I have to write b here, and this is 0, 0. I hope the video quality is good enough to see everything. Is it possible to see the letters everywhere? Okay, and again we show that our joint variables are here. So q2 is included here. So our joint variables can be identified. And the other parameters are geometric parameters. So b is fixed, it cannot change in time. And in the third case, there is no rotation. So the rotational matrix, the rotation matrix will be an identity matrix. So all the diagonal elements will be equal to 1. And the translational part is q3, and there is no anything else. Okay, so this is the third transformation. I hope everything is clear. And now we can go from here to here, from here to here, and here to there. So there is a transformation between the coordinate systems. But our goal is to express everything directly in the global frame. For example, we would like to have the position of the two center point in the global frame. So we need the transformation matrices, which transforms directly from any coordinate system to the global one. So we would like to go from 3 to the global, from 2 to the global, and of course from 1 to the global, which is ready. But if we multiply these two matrices, then the homogeneous transformation matrix, which transforms from 2 to 0, from the second to the global one, is obtained by just multiplying them. So that's why it is very efficient. I can multiply t10 with t21, and then I will obtain the homogeneous transformation matrix. I will just copy it. So the result will be q1 b 0. This part is always 0, 0, 0, 1. So q1 b 0. We can see that q1 and b appears here together, and the rotation part will be the same. Not the same. So these two rotations are multiplied together. So this will be a mixture of the two rotations. So it will be cosine q2 minus sine q2 0, sine q2 cosine q2 0, and 0 0 1. And basically we can check its meaning. So it means that if I want to go directly from the global to the second coordinate system, I have to travel q1 in x direction, and then I have to travel b in vertical direction, and I have to have a rotational angle of q2. It is clearly visible here. And then applying this and the third homogeneous transformation matrix, we can create the transformation directly from the third to the global one, which is just this previous one multiplied with T32, and the result will be something complicated. So this part is always the same, and we are multiplying an identity rotation matrix with this one here. So the result will be the same what we can see here. So the meaning, the physical meaning is that again, so this is the same as you can see here. So the two rotations of the second and the third coordinate frame is equal to each other. So that's why the rotational part is exactly the same. But the translational part will be something different. So this will be Q1B. It's always 0 in Z. And additionally, we will have some new terms, Q3 times cosine Q2 and sine Q2. And we can check this result by just looking the figure. So the position of origin 3 is really given by this vector. So this is Q1, so this is Q1, okay, so this is Q1, B, and then we have to travel Q3 times cosine Q2 in horizontal direction, and then in vertical we have to travel cosine Q2 times Q3. It's maybe much more visible here. Okay, so physically vector gives the position of the origin relative to the global frame. Okay, so this is the kinematic description, and if we have it, we can do any transformation what we have. We can calculate the position of any point in the global frame, and let's see some examples. Actually, the title could be written here. So these are the homogeneous transformation matrices for the homogeneous transformation matrices for the global coordinate system. Okay, so these are the homogeneous transformation matrices which transforms directly to the global one. And then, how to use these matrices? We can, for example, calculate the absolute position of the third, which will be quite trivial. So this will be the absolute position of point 0.03, and this is basically R03. So this is the position vector of point 0.03, given in the global frame. It means that the absolute. Okay, so absolute means that it is given in the global frame. So this is equal to the corresponding homogeneous transformation matrix multiplied with the position vector given in the third frame. Okay, so it is given in the local frame. So this is global or absolute, okay, position, and this is called local position vector, and the homogeneous transformation matrix is given here. But let's see how this vector looks like, and this is homogeneous representation of the vectors. There is always an additional 1 at the bottom, and then there will be 3 elements x, y and z. So in z this is 0, and in x and y this is also 0, because this is the origin of this coordinate system. So this is trivial that its position is 0 in its own coordinate system. And we will see that if you just multiply it, this vector with this matrix, then finally we will obtain this vector. So the position vector of point 03 is really this one, q1 plus q3 times cosine q2, and b plus q3 times sine q2, 0. And this is a homogeneous vector, so there is 1 at the end. Okay, so this is the position, and basically this is P3O. Okay, so we can say that this is the position vector of the origin. So this is the same meaning. Okay, and so it was just to show how it's worked. And there is another example. Okay, yeah, from here you can see that again, that if you take the homogeneous transformation matrix of any coordinate system, it will basically contain the rotational matrix of the same coordinate system, and also this position vector. And this is very important to know, that the homogeneous transformation matrix basically consists of the position and the orientation of the same coordinate system, and it is given in the zeros frame. Okay, and another example of the application of these homogeneous transformation matrices is to calculate the absolute position of the tool center point. Okay, absolute position of the tool center point, absolute or global position of the tool center point. So RTCP in the global frame is equal to the corresponding homogeneous transformation matrix. So we have to take the third, because the position of TCP is a fixed constant vector in the third coordinate system. So this RTCP given in the third coordinate system is a fixed constant vector. Okay, so T is known now, but we can show how it vector looks like. So RTCP in the third coordinate system will be something like 0 minus E and 0, because this is this position in the third is 0 in x direction, this is minus e in y direction, and it's on the plane of the whiteboard, so the z component is 0 again. And then if we do this multiplication, we will have some position vector which gives us the absolute position of the TCP. So this will be Q1 plus Q3 times cosine Q2, and Q1 plus Q3 times sine Q2, and the third component is 0. And additional, so this is so far the position of point O, and we will have some other terms if we do this multiplication. So the next term will be plus e times sine Q2 and minus, so in vertical we go in minus direction, minus e times cosine Q2. Okay, so the position in the global frame is really this one. We can check it by just looking the figure. And the other important thing again, that it includes the first joint variable, the second joint variable, and also the third joint variable. So we see that the position of the last link always includes all of the joint variables. But for example, if I just take the second coordinate system, its orientation position is just affected by Q1 and Q2, so up to the second joint parameters, and it, of course, it does not depend on the third joint parameter. So the position and orientation of the second link is just depend on Q1 and Q2, of course. This is always true for serial robots. Okay, so this is for kinematics. Please ask some questions if there is. And then now we move on to the dynamics. So now we finished the first iteration, which is the forward kinematics of the robot. I don't know if there is any question or not. Yeah, okay. And then let's go to the second iteration step of the Newton-Euler method. But first we will take an overview again. So the large title for now will be the dynamic equations for open loop kinematic chains or open loop robots. So this is the big title, dynamic equations. And then let's go to check what is the Newton-Euler recursion. So let's go for a reminder or overview. So first, okay, this is partially a reminder. So the first iteration was the so-called forward iteration, which is now done. But let's sum up again. So we have a serial robot. The zeroth link is fixed to the ground, and then there are some other links. And at the end there is a TCP usually. And the forward iteration means that we go in this direction, joint by joint, and we can calculate the position and orientation for each link. And what we have is is the position and orientation of each link. Okay, so this is, let's say, joint I here, and if we know all of the joint parameters, then we can calculate the position of each coordinate system in the global frame, and also the orientation, which is given by the rotational tensor. Okay, and we can show here that Q1, which is a joint coordinate, is related to the, sorry, Qi is related to joint I. It's always, they are always connected. So this is the forward iteration. So we know the joint variables. Okay, so we know each of the joint variables, and therefore we can obtain these homogeneous transformation matrices for each link, and they depend on the corresponding joint parameter and some other parameters. So we can always calculate these homogeneous transformation matrices, and then by using the neighboring homogeneous transformation matrices we can obtain the position of each link in the global frame and the orientation of each link in the global frame. So that's what we do. And one more step. So if we do the time differentiation, and if we have all of the joint variables Q, and also the speed of the joint variables, and also the acceleration of the joint variables, then we can obtain not only the position, but we also can obtain the velocity of the center of mass for each link, and also the angular velocity of each link in the global frame. Okay, so we know that if we know the position and orientation, then we are able to calculate the velocity and angular velocity, and basically they are usually put in a bracket because they together describe the velocities of each link. And then we can also, after another time differentiation and using the joint accelerations, we can calculate the acceleration for each each link center of mass, and we can also calculate the angular acceleration for each link. And these are necessary for the Newtonian equations, right? So these are needed for the dynamic equations. Actually, we also need the angular velocities. So these are necessary for the dynamics. And this is the forward iteration. So we can calculate the accelerations and velocities for each link or each rigid body. And let's see what is the backward iteration. So this was the reminder, and the new part is the backward iteration, in which we will talk about the torques and forces acting on the links, and therefore we have to draw some free body diagrams. So we cannot draw this figure anymore because we have to separate the rigid links from each other, because we have to draw free body diagrams. It will be a bit complicated, but we have to do this drawing. So this one, and let's say this one and that one. So this is the last one. Okay, so this is 1, 2, this is link number 1, link number 2, this is link number I, and this is link number N. This is the last one. Okay, it is the same here. So this is the last link with N, and this is the first with 1. And in the backward iteration, we will use the free body diagrams, and we will see that it is possible to go in this direction and to take, for first we take the last rigid body and we consider all of the external forces which acts on the robot, like the weight coming from the weight of the object which the robot grasps. Okay, so I can consider the weight of the sponge, and this gravitational force acts on the robot, acts on the last link of the robot, and then I will be able to calculate the joint torques and joint forces, and then the joint forces acting on rigid body N, the reaction can be put here on the previous joint, and therefore I can again calculate the joint forces here. So let's draw the figure. For example, for the first link we can draw something. So this is for example joint 1, and there is a joint force here F1, and also there is some joint torque M1, and this is the same, for example, for rigid body number 2. So this is F2 and M2, the joint force and the joint torque. But we know from the Newtonian laws that the reaction torque will be acting on the previous body. So this is minus M2 here, and this is minus F2 here. Okay, so this is the idea, and this is, of course, this is joint number 2 here, and this is also joint number 2, and this is the idea. So the neighboring forces are always known, and if I'm starting from here, I will be able to calculate the forces and torques, and of course at the same time there are some external forces. So for each rigid body there is a gravitational force, so this is M1 times the gravitational acceleration. This acts also here, this is M2 times the gravitation, and of course in the second link there is a reaction torque from the third link, which is not drawn here. This is minus M3 and minus F3 and so on. And the good thing is that the accelerations can be calculated from the forward iteration. So for each rigid body we also have the information about the acceleration of the center of mass. It's coming from the forward iteration, so the acceleration is known for each rigid link. This is the acceleration of C2 and so on. And we can also calculate or we can use this double arrow. So this is the angular acceleration for link number 1, this is the angular acceleration for link number 2. So we see that we have everything what we need for the dynamic equations of the robot. Okay, so let's go to the details. So we have what we have will be listed here. So we already have the position of each link and orientation of each link, and we also have the velocity for the center of mass of each link and angular velocity of each link, and we also have the acceleration for the center of mass of each link, and we also have the angular acceleration of each link. Okay, so this is what we have from the forward iteration. Okay. Okay, we have it from the forward iteration, all of these kinematic parameters, and we also have the external forces. So they are also given. For example, the gravitational forces, and if I have a load, it can act on the last link of the robot, and there can be also a torque coming from the load. It's usually acting on the last link of the robot. So they are also external forces and torques. And what we can calculate, we can calculate the joint torques and forces. We can calculate the joint forces and torques, which is basically 6 equations and 6 unknowns. 6 unknowns for each link. So always the corresponding joint torque and force is the unknown. And we know from dynamics that we have 6 equations, so it can be done. So we can create 6 Newton-Euler equations for each body. We will see soon, and we can calculate the joint force and joint torque for each link. Okay, so it is done for each link. And this whole thing is called iteration because we already had this step. So we come from the kinematic calculation, and then we can create the dynamic equations, and then if we have the dynamic equations, we are able to calculate the joint torques and joint forces. And if we have calculated the joint forces, we can calculate the accelerations again in the upcoming time step, and we can integrate our equations. And if we integrate the accelerations, then we will go back again to the forward iteration, because then we will have a new configuration of the robot. Okay, so the iteration thing is that we calculate the configuration of the robot, we take the forces and torques, we will have the acceleration, and we can calculate forward in time. So we will be in a new configuration, and then the whole thing has to be done again. So this is the idea. And now let's go into the details of these free body diagrams, if there is no any question. So I've stopped for a while just to wait for questions if there is some, but I think it's quite clear, so there is no new things. So you can use your knowledge from dynamics, and this means that there are just spatial rigid bodies, and the free body diagram is given similarly as in the dynamics course. It is just put together, and we are using the action-reaction law from Newton. So the neighboring joint forces are acting on both links. So I will clear this part of the table and the blackboard, sorry, and let's take again a closer look. So we will not have too much new information, but it helps us to understand better everything. So but we will create the equations. So we can take the link index I, and in general case there is link number I, and also there is a previous link, so it is cut, and this is I minus 1, and there is another link which is the upcoming link, which is I plus 1, and we will draw everything. So this link has a center of mass, of course. This is Ci, this is the center of mass. Okay, Ci is the center of mass point. It will be abbreviated with COM if we need it. And from the forward iteration we know that we have some acceleration, which is AI or ACI, and in the center of mass there's a force m times mi times the gravity vector. Okay, so this is what we have in the center of mass. And by the way, there is a vector which represents the angular acceleration of this link, and we have now everything in kinematics. And actually we also need the angular velocity for the Newton-Euler equations, and yeah, that's important. Everything is given in the global frame, okay? And then we have the joints of the link. So this joint will be Ji plus 1, and this joint will be Ji, and these joints also appear in the neighboring rigid bodies. So this is Ji, and this joint here in which they are joining each other is Ji plus 1. And the important thing is that this is the positive force and positive torque. So in Ji, in relation to link I, there is the joint force Fi, and there is also the joint torque Mi, and in the previous link there is the same torque and force multiplied with minus 1. So this is minus Mi here and minus Fi, and therefore we also know that in the second or in the upcoming link there is Fi plus 1. This is link I plus 1, so this is the positive force and the torque, and their negative version can be seen here. So this is minus Fi plus 1, and the torque is also acting in the opposite direction, minus Mi plus 1. So these are the forces from the neighboring objects, and I think yeah, and everything is, again, everything is given in the global frame, so everything is 0 here. It's kind of boring to show, but yeah, it's important. But actually it doesn't matter if it's just a vector, but yeah, it's better to represent them in the global coordinate system. So this is a general link, and to have a complete figure of the whole thing, we can also take the last link. So if we are talking about the last link of the robot, there is N. So everything will be the same, but there is no joint here, but there is only a joint here, so this is Jn, and of course there is another rigid body which is called n-1, and this rigid body is n, okay? And instead of the next link, there is the environment in which the robot has some contact. This can be the load or a wall or anything. So this is the environment, and the only difference is that we will apply here, so this will be here the positive force, this is the F load, because we are interested in the force which acts on the robot, so therefore it is positive here, and the torque, the loading torque which acts on the robot and on the environment. So we will not create the dynamic equations usually for the environment, so that's why it's minus here, so that's not so important. But everything is the same, okay, so we can just finish it. So this is Cn, there is the acceleration which is ACN, there is the angular acceleration epsilon n, and also the angular velocity omega n, and everything else, and the gravitational force which acts here, this is mn times g, and everything, and of course the joint forces and torques. So I don't want to, so this is exactly the same as before, but this part is different in case of the last link. Okay, so this is the picture, and we can actually create the, so now we are talking about both figures. So okay, so we will create the equations for this link number I, and everything will be possible to generalize for the last link. So now I get rid of this picture, and let's see the dynamic equations for link number I, and so there are 6 equations, I mean 6 scalar equations, and there are 6 unknowns, the 3 components of Fi and the three components of Mi, and they are given in the global frame. Actually these are just vectors, so we don't have to show that they will be represented in the global, so that's not so important here. Sorry for that. Okay, so we want to calculate these unknowns, and basically we will have the Newtonian equation, the Newton's law, which is the m times, this is the time derivative of the impulse, a change rate of the impulse of the link, but we know that the m is constant, so therefore we can say m times the acceleration, which is equal to the sum of the forces, and we have the force, so m times the acceleration is equal to the force, sorry, like this, acting on joint I, and the other force acting on in the next joint, so this is minus Fi plus 1, and we also have the gravitational force usually, so this is m times the gravitational vector. Okay, so this is these are the first 3 equations in vector form, and we have a bit complicated part in the next 3, because this is the Euler equation, and we will say that the change rate of the angular momentum, so this is the change rate of the angular momentum, is equal to the sum of the torques. But first let's detail it. So this is the change rate of the angular momentum, or rate of change. Angular rate of change of the angular momentum, and it's just equal to the mass moment of inertia matrix expressed in the global frame. That's not always very simple, times the angular acceleration for each link, plus it's also given in the global frame, plus we have this other term when we have to take the cross product of the angular velocity with the angular momentum, which is theta ci again times omega I 0. Okay, and this part is it's called P ci, which is the angular momentum. And if we take the time derivative of this whole thing, then we will obtain this formula for the rate of change of the angular momentum. So it's kind of complicated, but you also learned it in the dynamics course, so you can calculate everything here. And the other part of the equation is the sum of the torques or moments in the acting on the rigid body. So we see that there is Mi, which is a joint torque, and then we have minus Mi plus 1. And it's not enough, because we also have the torque of the forces, or moment of the forces. Fortunately, there is no moment coming from the gravitational force, but there is a moment coming from the joint force. So we will have a term which tells us that we have to take the position vector. I will draw it with green. So this is a position vector. This is R from the center of mass to Ji. Okay, this is a position vector. So this is RCI Ji, and we have to take the cross product with the force Fi, and everything is given in the global frame, and this is underlined from now. And we have the other term, which is RCI Ji plus 1. This is the vector here, the position vector of Ji comparing to the relative to the center of mass. So this is RCI Ji plus 1. So we have to take the cross product with the force acting here, Fi plus 1, and there's a minus sign here, which is important because this is minus. Okay, so these are the Newton-Euler equations, and it can be always calculated. So let's take an example where we check the details. So we go back to our planar example and show the dynamic equations. Okay, the same planar example again. I just create a sketch quickly. I don't want to. There's the time, so the figure is exactly the same what we had previously, but I will need it. So this is the the same robot what we had previously. Okay, this is the robot, and we need the free body diagrams for each rigid body. So the first rigid body is this one here. This is the first, this is the second, and this is the third here. So the first rigid body, free body diagrams. For the first rigid body, we have a free body diagram, and then there will be a free body diagram for the second rigid body. I need to copy it to this position because I need to save some free space. And this is the free body diagram for the second rigid body, and the third one looks like this. And in each rigid body, in each free body diagram, we have to show the center of mass first. So for the sake of simplicity, the center of mass will be equal to the origin in the case of the first rigid body. So the coordinate system is this one. This was x and y. The center of mass in the second rigid body will be here. And the coordinate system here was x2 and y2, and in case, so now it will be in the middle position, so it's not in the origin. This is O2, and in case of the third, again our center of mass will be equal to the origin. So this O3 is the same as the center of mass C3 for the sake of simplicity. And then you have to complete the figure. So there are torques and forces acting everywhere. So let's take the first drawing. So here there is the joint force which acts in horizontal direction and also in vertical direction. And also there is an unknown joint torque which is describing the action and reaction torque between the zeros link and the first one. So this is M1 torque. And we also need to draw the second joint forces. So the second link is connected to the first link in this point here. So therefore the second joint force will be here. So this is F2y. And this is F2x, and the opposite of these forces are acting on the first link. So I have to put here minus F2y because it acts downwards in this point, and F2x is actually acting here because they are connected to each other in this point. Okay, so this is the drawing for the first free body diagram for the first rigid body. Sorry for these separation lines, but yeah. And then we also know that there is a torque acting on the second body M2, and the reaction torque acts on the first body, of course. So these are the free body diagrams for the first and the second. And in the third, the forces are acting here and here. So we say that the F3xx here and F3y acts here, and there is the opposite, or the reaction force, F3y and F3x, and the position of this point where the force acts is basically represented by the coordinate Q3. Okay, so the position is given by the location of rigid body number 3. So this was the Q3 coordinate. And also there is a torque M3, and the reaction torque, which we can just put here. And there are also gravitational forces, so this is M1 times G, this is here M2 times G, and here we have M3 times G. So in each cases there is gravitational forces. And we should draw the accelerations also, but the figures would be too crowded, so I will just skip it, and we can take the accelerations by some equations. Okay, so, but if we want to calculate the acceleration for each center of mass, first we have to take the position of the center of mass point. Okay, so first we take the position of each center of mass point, and in the first figure we see that the position of the first center of mass given in its own local frame. Okay, it is very important. First we take the vector in its own local frame, which is 0 in each direction, because it's in the origin. But for the second rigid body, the center of mass given in its own local frame, so in the second one, it's in x2 direction, and the distance from the origin is L over 2 in x direction, so L over 2, 0, 0, okay? I hope it's clear. So we just create the position vector in its own coordinate system. And in the third case, it's very trivial again. So the position vector is in the origin, and from here we can transform it to the global frame. So we have to know everything in the global frame, so that's a 0 up there. So all of them should be calculated in the global frame, so therefore there is 0 in the left upper corner. And previously in the forward iteration we already calculated the homogeneous transformation matrices. Now we have to use them, because we can multiply the local position of the center of mass with the corresponding homogeneous transformation matrix. And here we see that the neighboring indexes are the same. Okay, that's important to see that. That's why I see that I didn't make it wrong. Okay, and you can just accomplish this calculation, and we will have very simple equation. Now we have to switch to homogeneous representation. In the case of the first center of mass, this will be, we can just check it visually, but we can multiply it, but it will be given by Q1, and in all of the other directions it will be in 0. I just show the global coordinate system. This is x0 and y0. This is the global frame where we want to express everything. And then we can do the same for the two other rigid bodies. So here the position will be Q1. Oops, it's not enough. So it's Q1 and b plus something, and the z component is 0. So it's L over 2 times cosine L2 over 2 times cosine Q2, L2 over 2 times sine Q2. This is the position. Okay, and this link has a length of L2. It was not introduced before. And something similar for the third ring. It's Q1 B0 and plus Q3 times cosine Q2 and Q3 times sine Q2. So these vectors gives us the positions of the center of mass for each rigid body, okay? And then we have to calculate the velocity for each center of mass. I will just show it how to do it. Now we can just simply time differentiate everything. So the center of mass velocity for the first rigid body is just simply Q1 dot 0, 0. Now we can get rid of the homogeneous form. And in case of the second, we will have for example here Q1 dot plus L2 over 2 times sine Q2, but this is minus, and there is minus, and there is also Q2 dot because of the chain rule, and then B time derivative 0, and we have L2 over 2 times the derivative of sine theta, which is sine Q2, which is Q2 dot times cosine Q2 because of the chain rule. And you can do the same, but this is homework for now, okay? You can simply calculate the time derivative. And if you have everything regarding the velocities, then you can also calculate the accelerations for each center of mass. For example, the first, so this is A. The velocity, so the acceleration for the first center of mass is the time derivative of this vector, so this is just Q1 double dot 0, 0. And then the acceleration for the second center of mass is a bit complicated because there are a multiplication of some terms. So this is Q1 double dot plus, this will be minus Q1 double dot minus L2 over 2 times Q2 double dot times sine Q2. So first I take the time derivative of this term and copy the other, and then I will copy the first term and take the time derivative of the second term. So Q2 dot comes out, therefore here we will have Q2 dot square. So this is related to some centrifugal force and centrifugal acceleration and so on. And we can also create the same for the second link. This will be minus L2 over 2 times Q2 double dot times cosine Q2, and plus we will have, well, why is it minus? It is not minus, this is plus, and this will be minus because the derivative of cosine is minus sine, so this will be L2 over 2 times Q2 dot times sine Q2 times Q2 dot again, so this is squared, and 0 in the z component. And you can do the same for the third rigid body. This is homework again. So you can create the kinematic, these are basically the kinematic equations what we need. So we have the accelerations, And we also need the angular accelerations. That will be much simpler. First we can take the angular positions, and then with time differentiation we can calculate the angular velocity and angular acceleration. So in case of the first, you can take the rotational matrices basically. You can take it out from the homogeneous transformation matrix. The first rotation matrix was 0, minus 1, 0, 1, 0, 0 and 0, 0, 1. And from this you can reverse engineer the angle, so the theta, sorry, we will introduce some new angle. So this is the absolute angle of rigid body number 1, which is it was pi over 2. Okay, this is the absolute angular position, and we know that if we create the time derivative, then omega 1 will be 0 because this is constant, and epsilon 1 will be also 0 because this is also constant. Okay, so we can just move into the direction of the accelerations and time derivatives. And you can take similarly the rotational matrix for the second body. But if you go back, you will see that it is exactly equal to the rotational matrix of the third body. And this is basically cosine Q2 minus sine Q2, sine Q2 and cosine Q2. And there is no rotation in Z. There is the rotation about the Z axis, so therefore this is 0, 0, 1. And from here you can see that the second and the third absolute angular position of the second and the third rigid body is exactly the same, and they are equal to the Q2, which is an angle. Okay, Q2 was an angle. It was measured here. This is Q2 angle. And therefore, you can see that omega 2, which is equal to omega 3, is Q2 dot, and epsilon 2, which is equal to epsilon 3, is Q2 dot, but this is double dot. Okay, so we are just taking the first and second time derivative, and we can obtain the angular velocity and angular acceleration. And now we have everything. So we have the acceleration for the center of mass of each rigid body, and we also have the angular velocity and angular acceleration for each rigid body. And now we can move on with the dynamic equations, which is the last step. Okay, so we can create the dynamic equations. And we can do it separately for the first, second and third rigid body. So we go one by one, and for the first rigid body it's quite simple. So if you go back to the acceleration, you will see that the acceleration in x direction was q double dot, q1 double dot, and it was 0 in y and z direction. So m times 0 is also 0. And yeah, and the third thing is that the angular acceleration was also 0 for the first body. And the first two equations are the sum of the forces, So in x direction we have f1x minus f2x. In the second direction, in the vertical direction, when there is no acceleration because it is constrained, there is a f1y minus f2y, and additionally we also have the gravitational force. So these are the sum of the forces, and we also have to take the sum of the torques acting on the center of mass. It's very important. We are calculating the sum of the torques acting on the center of mass. So we have positive m1 minus m2, and we also have the moment of f2x, which is positive. So this is f2x times parameter b, which is measured here. So this is the set of equations for the first rigid body, and then we have the set of equations for the second rigid body, of which the center of mass moves in a general way. So we can take the acceleration, what we have calculated before, and we also have to take the mass moment of inertia, which is also possible to calculate, right? Times the epsilon 2, and these things equal to the right hand side. So in the second case there is f2x here minus f3x, and in vertical direction there is f2y minus f3y minus the gravity m2 times g. And additionally we have some torques acting on the center of mass. So this is m2 minus m3, plus we will have basically the torque of the joint forces. So there is f2x times L over 2 times cosine q2. This is here. So this is f2x here, and this distance perpendicular to f2x is L over 2 times cosine q2, right? And we have the same for the y component. Sorry, this is sine q2, and this will be the cosine, and this whole thing together is basically the vector from the center of mass to joint 2 cross second joint force, okay? And additionally we also have the same term, which is this is J3 here, where they are, this is J3. We have to take the vector from the center of mass to J3, and we have to calculate the cross product with F3, which acts here, and what we have is F3x times Q3 times sine Q2 minus F3y times Q3 times cosine Q2, and this whole term is representing the torque of F3 acting on the center of mass. And the last thing is to create the same equations for the third rigid body. This is A3, sorry, C is missing here, AC2, and AC3 x component, AC3 y component, and epsilon 3, of course, z component. They are already calculated, and I have to get rid of these extra terms, and they are equal to f3x. And one very important thing is just missing from my figure, but this is important. So this is the x component of the load loading force coming from the environment. So in the TCP there is some forces acting from the environment. Okay, so environment acts here, and we also have a vertical component, so this is F load Y, and we also can have some torque coming from the environment. So this is the M torque, called M load, coming from the environment. So here we see that there is also the X component of the loading force, and in vertical direction it will be exactly the same, but everything is Y component, and additionally we have the gravity, and finally we have the sum of the torques. So there is the joint torque M3, and additionally there is the loading torque from the environment, and additionally we have the moment coming from the loading torque to the center of mass. So this is F load X times E times cosine Q2, and E is the length of this bar here, and additionally we have F load Y times E times sine Q2, and this whole term here is basically the vector going from C2 to the TCP, and cross product with the loading force. Okay, this whole term is calculated like this. So we have the Newtonian equations, and it's basically ready. We have just some closing thoughts about the solution of these equations. So we don't solve it, but we have to see how it can be done. And as you see, there are a lot of unknowns. So the unknowns are, so in these three equations we have 6 unknowns, F1, F2 and M1, M2. But if you take a look on the third set of equations, you see that the unknowns are only F3 and M3. Okay, so these are unknowns. And from these three equations you can solve them. Okay, so from the first set you can calculate F3x, F3y and M3. And then we can move on to the previous set, set of equations related to the second rigid body. From here, again, you can calculate your unknowns, these three, but we can show that there are also some unknowns, but they are already calculated from the third set of equations. So you can calculate the second joint force X component, second joint force Y component, and second joint torque. And from the first set of equations, from now it's quite trivial. So we already calculated these unknown joint forces and joint torques. And joint torque, there is just a single torque. And we can calculate our unknown parameters, unknown joint force parameters. And this is why we call it backward, because we start with the last link and go backward to the first. Okay, so this is backward because we go from, in general, we go from n to 1. And an additional thing is that we have to somehow obtain the joint torques and forces, or actuator forces and torques. actuator forces so if you take a closer look on the figures, so there is the first rigid body on which there is a joint force because it is a translational or prismatic joint, and we will call it U1. This is the this is the force which provides the motion in horizontal direction. The second rigid body is a rod, and your joint is a revolute joint, so therefore we should have some torque related to the control. So this will be U2, which is an actuator torque. And in case of the third, this is the third link. Again, the force is the actuator force follows the direction of this bar, and it's always parallel to the second bar. And this is a force basically, because here we have a rotational joint, sorry, a translational joint. And basically, if you compare the free body diagrams with the representation of the joint, the actuator force and torques, you can, I don't have the figure, but you have in the video and in your notes, so you can make a connection between them. So U1 is equal to the first joint force X component, U2 will be equal to the second joint torque, but so this is only the actuator part, and F2X, for example, and F2Y are constraint forces. They are not active forces, they are provided by the constraints. And here this is the same. So M1 and F1Y are also constraint forces. And U3 is equal to, here if you take the free body diagram, you will see that it will be equal to F3X times cosine Q2 plus F3Y times sine Q2. So you can calculate the actuator or motor forces. Okay, so actuator means motor forces or motor torques. So these are just the closing thoughts. We will go back to this problem later. So I don't know if there is any question or something. I hope it is not a technical problem, because Giuseppe Habib from our department also had the same problem. The comments didn't appear, but there is some question. X1. There's a question about the homework, but I will refer back that in the Facebook page. And there is a comment that in some figure X1 and Y1 was switched. Now it's not possible now to go back. Sorry for this technical problem. I don't know why the comments are delayed a bit. But if there is no question about this part, then I think we close this event. And of course, if you have further questions, or if you take the video later and if there are questions arising, you can ask in email, or you can ask in the Facebook page. Email is better, I think. So thank you very much for today, and sorry it was again a bit compact and hard task, but you have time to figure it out based on the video. And next time we will also have some examples and we will show everything again. So thank you very much.